Now that we understand message integrity, we're going to go back to the concept of encryption and look at how to combine encryption that's secure against eavesdropping with message integrity to get encryption that's actually secure against tampering and eavesdropping. It turns out that combining integrity and encryption is actually not so simple. In fact, there are many ways to do it, and some of them are correct and some of them are incorrect. So let's look at a couple ways to do it. So here we have an encryption key that's going to be used for eavesdropping secure encryption. And here we have an integrity key that's going to be used for message integrity. So K sub E, K sub I. As I said, there are many ways to do it, and it turns out practitioners actually implemented various ways, even though it turns out only one way is the absolute correct way to do things. So the first option, which is actually used in SSL, is the following. Take your message M, and then compute a MAC on the message M, and concatenate the tag to the MAC. And then finally encrypt, so the MAC is computing using KI, and then finally we encrypt the concatenation of the message and the tag using the encryption key KE, and that gives us the output. So this is sometimes called MAC then encrypt. We first MAC, then we encrypt. The second method, which is used in IPsec, is the following. Take your message M, encrypt the message M using the eavesdropping secure mechanism, like CBC encryption, say, with a random IV, of course, and then compute a MAC of the ciphertext. And the MAC is going to be transmitted in the clear now, the MAC of the ciphertext. This is called encrypt then MAC. And the third approach, which is used by SSH, is basically encrypt the message and then compute a MAC of the plaintext and append the MAC of the plaintext to the message. So it turns out only one of these three methods works for arbitrary combinations of encryption and integrity. Yeah, so let's try to reason through this. So the SSH mechanism by itself is actually not a good idea because the MAC algorithm is not guaranteed to not leak information about the message, right? The MAC itself could actually leak the first couple of bytes of the message as part of the MAC. Well, if we append that in the clear, then the attacker will learn something about our message. So the SSH method, I would strongly encourage you to actually not use. Now it turns out that between the SSL method and the IPsec method, actually the IPsec method is the preferable one. And the reason it is the preferable one is because intuitively what's happening here, we encrypt the message, so this block here reveals no information about the message, and then the MAC basically locks the ciphertext and ensures that no tampering has happened to the ciphertext. So in other words, when the recipient receives the message, the first thing he does is he checks that the message, that the ciphertext hasn't been tampered with, and then once he's assured no tampering took place, all he has to worry about is eavesdropping attacks, which is exactly what the eavesdropping confidentiality mechanism is intended to do. So in some sense, the MAC locks the ciphertext and prevents tampering on it, and that's why this is the preferred approach. Of course, you can rigorously argue that this satisfies a rigorous definition of authenticated encryption, but that's all been done, and that's the sort of proofs that we do in a crypto course. Now, the SSL story is kind of interesting. It turns out generic, this is not secure. In fact, there are message integrity mechanisms and encryption mechanisms where if you combine them together in the SSL method, you'll end up with a system that's actually not secure. However, for the specific encryption algorithms I told you about, namely counter mode and CBC encryption, the SSL method is a fine way to do things, but nevertheless, there's no reason to not use a generic solution, and so overall, the IPsec solution, kind of the encrypt then MAC, is the preferred way to do things, and I kind of gave you intuition as to why that's the case. Essentially locking the ciphertext from tampering, and then we only have to worry about eavesdropping, and that's what's being taken care of by the eavesdropping secure encryption. It turns out there's actually a number of standards for doing authenticated encryption. So authenticated encryption, I should mention, is the formal concept of an encryption scheme that provides both integrity and confidentiality. And there are a couple of standards that do this. And in practice, when you come to implement encryption, I would encourage you to only use one of these three standards. Okay, so the standards are basically, one is called CCM. This is used in 802.11i. So in your wireless network, CCM is basically a CBC MAC along with counter mode encryption. Then there's GCM, which is actually a very efficient way to do the encryption. This is basically counter mode encryption with a very efficient MAC. And so this is actually a good way to do things, except GCM actually involves a little bit of math, so the software implementation is actually bigger than the implementation for other modes. And finally, there's another mode called EAX. All three have been standardized. I should say these two have been standardized by the National Institute of Standards, whereas this one has been standardized by the IETF, the Internet Standards Body. And then EAX is also using counter mode encryption. You notice everybody prefers to use counter mode encryption because of the parallelism and so on. And EAX actually uses a different type of MAC called OMAC, which I won't explain here. Now, all these modes actually support this extension called Authenticated Encryption with Associated Data, where the idea is that often you don't want to just encrypt and authenticate data. Often you want to send a packet where the body of the packet should be encrypted and authenticated, but the headers of the packet should actually be sent in the clear. And they should just be authenticated to make sure nobody tampers with them, but they shouldn't be encrypted. This header is often called associated data, and all these modes basically support authenticated encryption with associated data, meaning that the whole thing is authenticated. In other words, an attacker can't change anything, but only the encrypted part is encrypted. The associated data is actually sent in the clear. So I just wanted you to make aware that these standards exist. Now, the funny thing about these standards, you realize, is you somehow, so both in CCM and in EAX, you have to do PRF operation once for encryption. Once for counter mode encryption, you do a PRF operation, and once you do a PRF operation for a CBC MAC. In other words, the number of PRF operations for a message of n blocks is actually 2n. 1n for encryption and 1n for integrity. 2n. So it's twice, you apply the PRF twice as many times as necessary to get both integrity and confidentiality. It turns out there's a beautiful mode called OCB. It's actually relatively recent. It was designed after the year 2000. And this OCB mode basically provides both integrity and authentication. In other words, it provides authenticated encryption using just one application of the PRF per message block. And I kind of wrote down a schematic of how OCB works. You can see there's a masking function, just like in PMAC. There's a masking function before the PRF, but there's also a masking function after the PRF. And you can see that all these operations are actually done in parallel. So if you have three processors, one processor can be applied to the first block, the second processor to the second block, third processor to the third block, and so on. And finally, there's a checksum that's computed, and this is actually the integrity check that's checked before the ciphertext is actually decrypted. So OCB is a more efficient mode than these three standards. So one would ask, how come OCB is not a standard? And the answer is typically, as usual, it's because of patents. There are multiple patents protecting this idea, and so it was actually difficult to get these to be standardized. So to conclude this module on symmetric encryption, I want to say a few words about the real world. The first one is that really implementing crypto systems is extremely tricky. Even if you understand the theory of how the crypto systems are designed, getting the implementation right is very difficult. And in fact, you might fool yourself into thinking that your system is secure, but in fact your implementation would leak the secret keys. And a nice example of that is something called power cryptanalysis. Let me explain what that means. So it turns out, of course, that the amount of power consumed by the CPU depends on the actual instruction that the CPU does. And in fact, it even depends on the data that's given to the CPU. So the idea in this power cryptanalysis is to measure very accurately how much power is consumed by the processor at every given microsecond. And then you can kind of draw this diagram of the amount of power consumed every millisecond. And you can see very clearly, this is an example of an implementation of DES. So you can see very clearly the 16 rounds of DES are very clearly represented in this diagram. And in fact, it turns out if you zoom in, you can literally read off the bits of the DES secret key just by looking at the diagram. Okay, so this is an example where, in fact, the implementation wasn't careful about hiding its power consumption. As a result, this was particularly attacked an implementation on a smart card. So the attacker would steal the smart card from you, and then he would plug it into this power meter and produce a diagram like this, and then he can very easily just read the secret key from the smart card. So because of this, now all smart cards try to defend themselves against power cryptanalysis. But again, it shows you that until people realize that this is a serious attack, nobody was defending against it. And as a result, even though the math was correct, the crypto math was correct, the implementation was completely vulnerable. And there are similar attacks like timing attacks, where if I measure the time that it takes to run a certain operation, I can actually eventually recover the secret key. And there's this nice example where if I measure the time that a web server takes to set up an SSL tunnel, I can actually extract the server's secret key just by measuring this timing information. And so again, if you're not careful about your implementation may leak side information, and these side channels could actually reveal your secret key. And finally, I wanted to talk about randomness. We kept talking about random keys and random nonces and random IVs. The question is, where does all this randomness come from? So I just wanted to mention that there are also standards on how to generate randomness. In fact, this is a document from the National Institute of Standards that explains how to generate randomness. And essentially the way this works is as follows. The random number generator is going to have some internal state that it keeps around, and then it's going to collect entropy from the system. We'll talk about where this entropy comes from in just a minute. But then essentially there's like this internal state is being fed into some sort of pseudo-random generator, and that actually generates the final output. Okay, so there's true entropy being collected into this internal state, and then this internal state is kind of cleaned, because the problem is with state entropy that's collected by listening to various computer events, it might be biased in various ways, and the pseudo-random generator is used to kind of extract the real entropy out of this biased entropy, and then that's actually the thing that's output from the generator. Okay, so there's in Unix, I would encourage you, actually, there's a virtual device called dev/random. You can very easily just type, cat dev/random, and you'll see it produce a random output for you. And the way dev/random generates its entropy, where does it collect its entropy? Basically, it's constantly measuring entropy of the system, adding it to its internal state. And it collects it basically from two sources. One is hardware interrupts. So every time you hit a keyboard, every time you move your mouse, that generates a hardware interrupt. And what dev/random does is it measures the time at which these interrupts took place, and then adds that entropy at that time to its entropy pool. And then just recently, actually, Intel announced that it's adding hardware random number generator to its Ivy Bridge processors. In fact, there'll be a read randomness command that generates randomness at an incredible speed, 3 gigabits per second. So there'll be enough randomness on the processor, that as much as you want, and you can use that to generate random IVs, you can use that to generate keys, and so on. So this is how randomness is generated in practice. And so just to summarize, symmetric encryption, basically symmetric encryption is used for secure communication and secure document encryption. We talked about eavesdropping security, just eavesdropping security, and that should not be used by itself. We talked about two modes, CBC and counter modes, as well as stream ciphers. The difference was you could either use them as one time or many time. Yeah, there are different modes depending on whether you use them as a one time or a many time. Here you can use a fixed IV. Here you had to use a random IV or a many time key. And then we talked about integrity, and we talked about authenticated encryption. And the reason I circled integrity and authenticated encryption is really these are the only modes that you should be using in practice. If what you're trying to protect is non-confidential, but you want to make sure nobody tampers with it, you use an integrity mechanism. If what you want to protect has to be confidential, you would use authenticated encryption. So you would always include integrity in the encryption process. It's very, very important. These things should never, ever be used standalone. I'll even do it in red to make sure you guys understand. These things should never, ever be used alone. You should either only be doing integrity or authenticated encryption.